Article 230.95 of the National Electrical Code requires ground fault protection, abbreviated GFP, for services rated 1000 amps or more. There is an exception to this rule, specifically for existing services that were installed before the National Electrical Code required GFP. However, in this situation, the existing meter main does not have GFP. Consequently, an update to the main with GFP is required. The California Building Code, specifically Chapter 34 on existing structures, allows for additions, alterations, or repairs to be made to any building or structure without requiring the existing building or structure to comply with all the requirements of the California Building Code. This is permitted provided the addition, alteration, or repair conforms to that required for a new building or structure. However, this exception does not generally apply to safety-related issues such as ground fault protection. Ground fault protection is essential for mitigating potential hazards and ensuring compliance with prevailing safety standards. Therefore, an update of the main with ground fault protection is necessary to comply with the National Electrical Code and to ensure safety. Ground fault protection systems are designed to detect and interrupt ground faults, which are unintended electrical connections between a live conductor and ground. These faults can occur due to insulation breakdown, equipment failure, or accidental contact. Without ground fault protection, these faults can lead to dangerous electrical shocks, equipment damage, and even fires. The National Electrical Code mandates ground fault protection for large electrical services to minimize these risks. When upgrading or modifying an electrical service, it is crucial to assess the existing equipment and ensure it meets current safety standards. In the case of a meter main without ground fault protection, an upgrade is necessary to provide adequate protection against ground faults. This upgrade typically involves installing a ground fault relay and a current transformer that monitors the current flowing to ground. If a ground fault is detected, the relay trips the main circuit breaker, interrupting the flow of electricity and preventing further damage or injury. It is important to note that ground fault protection is not a substitute for proper grounding. Grounding provides a low impedance path for fault current to flow back to the source, which helps to quickly trip the circuit breaker and clear the fault. Ground fault protection is an additional layer of protection that can detect and interrupt ground faults that might not be detected by the grounding system alone. When selecting a ground fault protection system, it is important to consider the specific requirements of the application. The system should be properly sized for the electrical service and should have a sensitivity level that is appropriate for the type of equipment being protected. It is also important to ensure that the system is properly installed and tested to ensure it is functioning correctly. Ground fault protection systems should be inspected and tested regularly to ensure they are in good working order. This includes visually inspecting the equipment for any signs of damage or wear, and performing functional tests to verify that the system is tripping the circuit breaker when a ground fault is detected. Regular maintenance and testing can help to ensure that the ground fault protection system is providing adequate protection against ground faults. In summary, ground fault protection is an essential safety feature for large electrical services. When upgrading or modifying an electrical service, it is important to assess the existing equipment and ensure it meets current safety standards. If the existing equipment does not have ground fault protection, an upgrade is necessary to provide adequate protection against ground faults. This upgrade should be performed by a qualified electrician who is familiar with the National Electrical Code and ground fault protection systems. The absence of ground fault protection in an existing electrical system presents a significant safety hazard. Ground faults, which are unintended connections between a live conductor and ground, can lead to electrical shocks, equipment damage, and fires. The National Electrical Code recognizes this risk and mandates ground fault protection for large electrical services to mitigate these hazards. When an existing electrical system is undergoing modernization or renovation, it is an opportunity to bring the system up to current safety standards. This includes installing ground fault protection if it is not already present. While there may be arguments for grandfathering existing systems, the safety benefits of ground fault protection outweigh the costs of upgrading the system. Ground fault protection systems work by monitoring the current flowing to ground. If the current exceeds a certain threshold, the system trips the main circuit breaker, interrupting the flow of electricity and preventing further damage or injury. This threshold is typically set at a level that is high enough to avoid nuisance tripping, but low enough to detect and interrupt dangerous ground faults. The installation of ground fault protection systems should be performed by a qualified electrician who is familiar with the National Electrical Code and ground fault protection systems. The electrician should select a system that is appropriate for the electrical service and the type of equipment being protected. The electrician should also ensure that the system is properly installed and tested to ensure it is functioning correctly. Ground fault protection systems should be inspected and tested regularly to ensure they are in good working order. This includes visually inspecting the equipment for any signs of damage or wear, and performing functional tests to verify that the system is tripping the circuit breaker when a ground fault is detected. Regular maintenance and testing can help to ensure that the ground fault protection system is providing adequate protection against ground faults. In addition to the safety benefits, ground fault protection can also help to reduce equipment damage and downtime. By quickly interrupting ground faults, ground fault protection systems can prevent equipment from overheating and failing. This can save businesses money on repair costs and lost productivity. In conclusion, ground fault protection is an essential safety feature for large electrical services. When modernizing or renovating an existing electrical system, it is important to install ground fault protection if it is not already present. This will help to protect people from electrical shocks, prevent equipment damage, and reduce downtime. The National Electrical Code, Article 230.95, provides specific requirements for ground fault protection of equipment. These requirements are intended to enhance electrical safety by minimizing the risk of ground faults leading to electrical hazards. This section generally applies to service disconnecting means rated 1000 amps or more for solidly grounded wire electrical services of more than 150 volts to ground, but not exceeding 600 volts phase to phase. Ground fault protection is not required for services of less than 150 volts to ground. The primary purpose of ground fault protection is to reduce the likelihood of equipment damage and fire hazards that can arise from ground faults. It operates by detecting imbalances in the current flowing through the service conductors. A ground fault is an unintentional electrical path between a live conductor and ground, which can occur due to insulation failure or accidental contact. When a ground fault occurs, a portion of the current flows through an unintended path to ground, creating an imbalance in the system. Ground fault protection equipment senses this imbalance and, if it exceeds a predetermined threshold, trips the service disconnecting means, interrupting the flow of electricity and mitigating the potential hazards. The tripping threshold for ground fault protection is typically set lower than that of conventional overcurrent protective devices, such as circuit breakers or fuses. This allows the ground fault protection system to detect and respond to ground faults more quickly, minimizing the potential for damage or injury. The National Electrical Code provides specific guidelines for the selection, installation, and testing of ground fault protection equipment. These guidelines are intended to ensure that the equipment is properly designed and installed to provide effective protection against ground faults. Some key considerations in the selection and installation of ground fault protection equipment include the following. Firstly, the equipment must be listed and labeled for its intended use. This ensures that the equipment has been tested and certified to meet applicable safety standards. Secondly, the equipment must be installed in accordance with the manufacturer's instructions. This is essential for ensuring that the equipment is properly connected and functioning correctly. Thirdly, the equipment must be tested after installation to verify that it is operating as intended. This testing should be performed by a qualified electrician who is familiar with ground fault protection systems. In addition to the installation requirements, the National Electrical Code also specifies requirements for the maintenance and testing of ground fault protection equipment. These requirements are intended to ensure that the equipment remains in good working order throughout its service life. Ground fault protection equipment should be inspected and tested periodically to verify that it is still functioning correctly. The frequency of these inspections and tests will depend on the specific type of equipment and the environment in which it is installed. It is important to keep accurate records of all inspections and tests performed on ground fault protection equipment. These records can be used to track the performance of the equipment and identify any potential problems. The National Electrical Code also includes exceptions to the ground fault protection requirements in certain situations. These exceptions are intended to address specific circumstances where ground fault protection may not be necessary or practical. For example, ground fault protection is not required for fire pumps. Fire pumps are essential for providing water to fire suppression systems, and it is important to ensure that they remain operational during a fire. Ground fault protection could potentially cause a fire pump to shut down if a ground fault occurs in the system, which could compromise the fire suppression efforts. The National Electrical Code also allows for the use of alternative methods of ground fault protection in certain situations. These alternative methods must be approved by the authority having jurisdiction and must provide an equivalent level of protection. For example, the National Electrical Code permits the use of a ground fault circuit interrupter, abbreviated GFCI, instead of ground fault protection on certain branch circuits. Ground fault circuit interrupters are designed to protect individuals from electrical shock by detecting and interrupting ground faults that could cause a dangerous level of current to flow through the body. In summary, the National Electrical Code, Article 230.95, provides specific requirements for ground fault protection of equipment. These requirements are intended to enhance electrical safety by minimizing the risk of ground faults leading to electrical hazards. It is important to understand and comply with these requirements to ensure the safety of electrical systems. The specific requirements for ground fault protection depend on several factors, including the voltage and current rating of the electrical service, the type of occupancy being served, and the presence of certain types of equipment. In general, ground fault protection is required for solidly grounded alternating current services with the main disconnecting means rated 1000 amps or more and operating at more than 150 volts to ground, but not exceeding 600 volts phase to phase. This requirement applies to various types of occupancies, including commercial, industrial, and institutional buildings. However, there are some exceptions to this rule. For example, ground fault protection is not required for services supplying only fire pumps, or for services that are used exclusively for emergency systems. Additionally, ground fault protection is not required for certain types of equipment, such as electric furnaces and welding machines. The type of ground fault protection system that is required depends on the specific application. The most common type of ground fault protection system is a ground fault relay, which consists of a current transformer, abbreviated CT, and a relay. The current transformer is installed around the service conductors and monitors the current flowing through them. If a ground fault occurs, the current transformer will detect an imbalance in the current and send a signal to the relay. The relay will then trip the main disconnecting means, interrupting the flow of electricity and clearing the fault. Another type of ground fault protection system is a ground fault circuit interrupter. Ground fault circuit interrupters are designed to protect personnel from electrical shock by detecting and interrupting ground faults that could cause a dangerous level of current to flow through the body. Ground fault circuit interrupters are commonly used in residential and commercial applications, particularly in areas where there is a high risk of exposure to moisture, such as bathrooms, kitchens, and outdoor areas. When selecting a ground fault protection system, it is important to consider the following factors. Firstly, the system must be listed and labeled for its intended use. This ensures that the system has been tested and certified to meet applicable safety standards. Secondly, the system must be properly sized for the electrical service. This means that the current transformer and relay must be capable of handling the maximum current that could flow through the service conductors. Thirdly, the system must be installed in accordance with the manufacturer's instructions. This is essential for ensuring that the system is properly connected and functioning correctly. Once the ground fault protection system has been installed, it is important to test it regularly to ensure that it is operating properly. This testing should be performed by a qualified electrician who is familiar with ground fault protection systems. The testing procedure typically involves injecting a simulated ground fault current into the system and verifying that the relay trips the main disconnecting means. In addition to testing, it is also important to perform regular maintenance on the ground fault protection system. This maintenance should include visually inspecting the equipment for any signs of damage or wear, and cleaning the equipment to remove any dirt or debris. By following these guidelines, it is possible to ensure that ground fault protection systems provide effective protection against electrical hazards. The absence of ground fault protection in an electrical system can have serious consequences. Ground faults can cause electrical shocks, fires, and equipment damage. In some cases, ground faults can even be fatal. The National Electrical Code requires ground fault protection in certain situations to minimize these risks.